36, dilations. We're going to dilate a line segment by making it longer or shorter in the ratio given by the scale factor. You'll be able to verify experimentally the properties of dilations given by a center and a scale factor. And lastly, we'll be able to define dilation. Let's start with the task. Draw a triangle by plotting points A, 1, 3, B, 5, 3, and C, 5, 1 in a coordinate plane. Then draw and label triangle ABC. Step 2. Draw rays. Using the origin as the endpoints O, draw OA, OB, and OC. Step 3. Draw equal segments. Use a compass to mark point D on OA so that OA is equal to OB. Mark point E on segment OB so that OB is equal to BE. And mark point F on OC so that OC is equal to CF. Now draw a triangle DEF. Measure AB. 4. Measure BC. 2. Measure DE. 8. And EF. 4. Calculate the ratios. DE to AB and EF to BC. So DE is 8. EF is 4. AB is 4. And BC is 2. All of these ratios are going to simplify to the same. 8/4, 4/2, both simplify to 1/2. Using this information, show that the two triangles are similar. Okay, so we've got a couple of sides that are proportionate. So let's write that down. Since DE to AB is the same proportion as EF is to BC, corresponding sides are proportional. Each of them were 1/2 of the other. Here's a little symbol for triangle. Also, angles E and B are 90 degrees. So if you look at the diagram, the blue segments correspond to each other. The yellow segments correspond to each other. And angle E and angle B correspond to each other. Then we can say that these two triangles are similar because of the side-angle-side similarity theorem. So therefore, triangle ABC uses symbol for similar is similar to triangle DEF by side, angle, side. And we need to say similarity theorem because we're not saying that they're congruent. They're similar. Their angles are congruent, but their sides obviously aren't. Repeat the steps to triangle GHJ so that 3 times OA equals AG, 3 times OB equals BH, and 3 times OC equals CJ. I don't have enough room on the screen to do this, but I'd like you to continue on your notes. Let's define dilation. A dilation is a transformation that stretches or shrinks a figure to create a similar figure. If we look at the picture to the right of your screen, we can see that they look very much alike, but very different. Obviously, triangle ABC is much smaller than triangle XYZ. However, if we were to measure, we'd find that angle A is the same size as angle X. Angle B is the same size as angle Y. And angle C is the same size as angle Z. So their angles are all congruent, but their sides obviously aren't. Let's look at some coordinate notation for a dilation. So in other words, when you are on a graph, you can describe a dilation with respect to the origin with notation xy dilating to kx, ky, where k is a scale factor. So xy are your original coordinates, or your original points, and ky are your new or your dilated points. If k is a fraction between 0 and 1, then that's going to make things smaller. It'll be a reduction in size. So for example, if I have the original point as 1, 2, and I want to have a dilation factor of 1/2, then I'm going to take 1/2 times 1 and 1/2 times 2 to come up with my new points. And that'll lead me to 1/2, 1 on the graph. If k is bigger than 1, then the dilation is an enlargement. So I took those same original points, 1, 2, and k was 4. Then I'm going to multiply each of those original coordinates by 4 to get my new or my dilated coordinates. So that would lead me to 4, 8. Example, draw the dilation from x comma y to 2x comma 2y of the quadrilateral ABCD with vertices A 2, 1, B 4, 1, and C 4, negative 1, finally D 1, negative 1. And write the coordinates of dilation. Draw the original and final quadrilaterals. So I'm actually going to do this in the reverse order. I like to write the coordinates first and then do my graphing. So let's see. It says that I'm going to multiply both x and both y by 2 because there's a 2 in front of the x and a 2 in front of the y. So multiply x and y by 2. Now sometimes those numbers are different. Sometimes it might say 2x and 3y, in which case you would multiply the x by 2 and the y by 3. But in this case, it's 2 for both of them. So let's see. 2 times 2 that's going to become 4. And 1 times 2 is going to become 2. And we're going to do that for all these points. And by the way, I just named these new points L, M, N, P. So these right here, the L, the L, the M, the N, and the P, I just made those letters up. You can call them anything you want unless they give them to you specifically. So multiplying the B, 4, 1, each of those by 2, I'm going to end up with 8, 2. And C, 4, negative 1, so 4 times 2 is 8. And negative 1 times 2 is 2. And P, 1, negative 1, each of those by 2, I'm going to end up with 2, negative 2. Now I'm going to graph. I'll graph my original quadrilateral ABCD first, and then my new quadrilateral or my dilated quadrilateral LMNP. And I'm going to label the points as I go along. So here's my original quadrilateral ABCD. Now I'm going to draw the dilated quadrilateral by plotting these points. And my new quadrilateral LMNP, just by visual inspection, looks like it is the dilated figure from my original. So let's just do a spot check on some easy sides. Let's see. I've got 2 along BC. Let's compare that to what MN is. 1, 2, 3, 4. So that looks like a dilation factor of 2. Now remember, all of these have to be the same dilation factor or else we've made a mistake. So DC appears to be 3. So if I've done this right, PN should be 6. So let's see, 1, 2, 3, 4, 5, 6. It is. And the other easy to check is AB. AB is 2. And that should be 4. Let's see, LN 1, 2, 3, 4. It is. So it looks like I have done a good job of checking because all of my dilations, all of my sides have the same dilation factor of 4. I didn't check the side that didn't have a vertical or horizontal line because I have to use a distance formula, and truthfully, I think we're pretty dang close with the 3 axis. Okay, next example. It says a triangle has vertices A of 4, negative 4, B 8, 2, and C 8, negative 4. The image of ABC after a dilation with a scale factor of 1/2 is DEF. So in this case, our K is 2, and we're going to make a smaller shape or triangle than the original. So K equals 1/2. So the new triangle will be smaller than the original. Okay, so in this case, I'm going to multiply all of my original points by half. Okay, so 1/2 of 4, -4, will become 2, -2. 1/2 of 8, 2 will become 4, 1. And 1/2 of 8, -4 will become 4, -2. Okay, so let's go ahead and graph both my original and my new triangles. Okay, so here's my original triangle, triangle ABC. Okay, now we have everything graphed. Let's go ahead and verify that they're similar, just like we did in the last exercise. So let's see. I'm going to look at side DF. That corresponds to side BC, and we're going to check out what the difference of their two side lengths are. So let's see. EF, 1, 2, 3. And BC, 1, 2, 3, 4, 5, 6. So if we've done this correctly, the other side that we look at should be similar. So let's look at side DF and AC. So DF is 2, and AC, 1, 2, 3, 4. So it looks like when I compare these corresponding sides that I have a scale factor that is consistent of 2. Now let's look at angle F and angle C. That's the angle between the two sides we just compared. Now since angle F and angle C are both 90-degree angles, we can use the same reasoning that we did for our last justification. So, because, we'll go ahead and talk about the ratios. The ratio from EF to BC is the same as the ratio from DF to AC. First means that's proportional. Corresponding sides are proportional. Also, angle angle F and angle C are 90-degree angles. So, triangle ABC is similar to triangle DEF by the side angle side. And again, you must state the similarity theorem. It's not the theorem for congruence. They're obviously not the same triangle. You're making your own photo stickers. Your original photo is 4 inches by 4 inches. The image on your sticker is 1.1 inch by 1.1 inch. What is the scale factor of this reduction? So let's go ahead and label these. Here's my original picture. So this is 4 inches by 4 inches. And my sticker, once I put my photo on my sticker, I now have a reduction, and I'm down to 1.1 inch to 1.1 inch. Okay. So we're getting smaller. We have a reduction. So if I have a reduction, my scale factor needs to be a fraction between 0 and 1. Okay, so let's go ahead and set up a ratio of a side length of the sticker image to a side length of the original photo. So because we want to have this fraction, we want to have the smaller dimension on the top. And that's actually going to be our new sticker size. And so that is 1.1. And we want to put that over our larger dimension, which is our original photo. So our original is 4. So go ahead and simplify that in your calculator. You will get that this is an 11/40th reduction. That's our scale factor. That's our K. Okay, let's look at this task. You want to create quadrilateral EFG that is similar to quadrilateral PQRS. What are the coordinates of H? So it looks like we are missing a letter here. So let's go ahead and fix that in this original example. All right, so let's look at the corresponding parts. So let's see. I'm looking at this shape here with a little bend on the bottom of it between R, Q, and P. And it looks like R corresponds to G. So R is at the point 0, 2. And G is at the point 0, 6. So we've got R. That's 0, 2, and that is corresponding to point G, which is 0, 6. So it looks like a dilation factor. Remember, the dilation factor is denoted with a lowercase k. It looks like from R to K is getting 3 times bigger. Let's look at one other factor that we know. It looks like P, these points right here, corresponds to E. So P is at the point 3, 0. And E is at the point 9, 0. So let's just write this over here. So P, which is at the point 3, 0, is getting dilated to point E, which is at the point 9, 0. And again, it looks like the dilation factor is 3. We could check point Q and point F, but I think right now with 2 points verified to have the same dilation factor, we can go on and say that we're going to use 3 as our multiplier. Now, H is going to correspond to S somewhere out here. Okay. So we're going to take that point S, and we're going to go and multiply it by 3 to find H. So S right now is at the coordinate 4, 5. And we want to dilate it by a factor of 3. Okay, so then we'll just multiply each one of the coordinates by 3. So I will have H, which will be whatever 4 times 3 is, and whatever 5 times 3 is. So it looks like H is going to be at the point 12, 15. It doesn't ask us to graph it, so we'll just leave it at that. So this is guided practice. Determine whether the dilation figure from A to B is a reduction or an enlargement, and then find its scale factor. Okay, so let's look at A. So from A to B, well, A is definitely bigger than B, so this is a reduction. Let's go ahead and look at some of the coordinates. So on the end here, A is at the point 0, 2. And at the other end, 1, 2, 3, 4, 5, 6. Two. B has endpoints 0, 1 and 3, 1. So down here in the work area, I created a little chart. I'm going to put the A points, 0, 2, and 6, 2 under A. And then the corresponding points in the B column. So 0, 2 corresponds to 0, 1 for B, and 6, 2 corresponds to 3, 1. So now let's look at their scale factors and compare each value to make sure it's consistent. So originally, it looks like I'm going from 2 to 1. Now remember, this is a reduction, so I want a smaller number on top. So I'm going from 2 to 1, so this is a reduction of 1/2. And now let's look at the rest of the values. So from 6 to 3 is also getting reduced by 1/2. And from 2 to 1 is also being reduced by 1/2, so we can be pretty sure that our scale factor is 1/2. All right, let's look at B. Okay, so going from segment A to segment B, obviously is an enlargement. And I've labeled the points on the graph. So all I need to do is list and compare and make sure that everything is consistent. So the 2 points in A, segment A, are 4, 2, and 0, 2. Those correspond to points 6, 3 on segment B and 0, 3. Now, this is an enlargement. A is smaller than B, so we want the bigger number to be on top. So let's first look at the difference between 4 and 6. So it's hard to tell exactly what is increasing there. So I'm just going to go ahead and create the fraction 6 over 4. So I'm creating that from just the x coordinates because I can't tell immediately what I multiply by. Now we'll look at these second coordinates. 2 to 3. Again, can't tell immediately what to multiply by. So I'm going to go again and put the larger number on top. 3 over 2. Well, this is kind of interesting because the 6 over 4 will actually simplify to 3 over 2. So that looks promising so far. It looks like our scale factor might be 3/2. Let's look at the next set of coordinates. Well, from 0 to 0, nothing's happening. Can't really tell. But look, those y coordinates now are from 2 to 3. Again, it's an enlargement. So with the larger number on top, definitely now can say that we have a scale factor of 3/2, or if you want to say 1.5 or 1.5, you can do that as well. Because sometimes you're going to have scale factors that are fractions. Let's go look at these last 2 diagrams, and I'd like you to try these on your own. And then come back and check to see if you've got the same thing that I've got. Okay, so I'm labeling my corresponding points. In triangle A, 1, 2 corresponds to 3, 6 in triangle B. In triangle A, 3, 2 corresponds to the point 9, 6, and 2, 0 corresponds to the point 6, 0. Now, going from triangle A to triangle B is definitely an enlargement, which means I want a number that is bigger than 1 for my scale factor. So I'm going to do the easiest one first, and that's the bottom one. Going from 2 to 6 looks like a scale factor of 3. All right, so that's the easiest one. Let's go back up to the top. Going from 1 to 3 is a scale factor of 3. And from 2 to 6 is a scale factor of 3. So far that's pretty consistent. Let's go ahead and look at the last one. So I'm going from 3 to 9, that's a scale factor of 3. And from 2 to 6, that's also a scale factor of 3. So now we verify that, in fact, to go from triangle A to triangle B, I have to scale all my coordinates by 3. So let's do this last quadrilateral, and then we'll buy the last example. So try it on your own, and then look up to see if you've got the same thing that I have. Okay, after labeling my triangle, I find that, after labeling my quadrilateral, I find that the point negative 3, 3 is corresponding to quadrilateral B, negative 1, 1. 6, 0 corresponds to 2, 0. 6, -3 corresponds to 2, -1. And -6, -3 corresponds to -2, comma 1. And this is a reduction. We're starting off with quadrilateral A, which is this blue large quadrilateral. And then we're ending up with quadrilateral B, which is a small pink one. And one of the things I added to all of our work boxes is little things that I think are a good way to start. If you have a reduction, you should tell yourself, I should have a fraction smaller than 1. And if I have an enlargement, I should have a number greater than 1. So we have a reduction in part D, so we should have a fraction that is smaller than 1. So let's go ahead and look at the easiest first. Going from 6 to 2 is a reduction of 1/3. Again, I'm going to put the smaller number on top, so I can put 2 over 6. And I can simplify that to 1/3. Okay, so let's go look at some of these other ones. So on top here, I am going from this -3 to -1, and from +3 to 1. So again, it looks like I have a reduction of 1/3. By the way, we don't ever want to use negative numbers when we're talking about reductions or enlargements. That doesn't make very much sense because we're only talking about something getting bigger and something getting smaller. So we're talking about distance. Let's look at the third set of points. From 6 to 2, again, is 2 6. And from -3 to 1, again, is 1/3. So everything's simplifying to 1/3. And in this last example, again, from 6 to 2, we want the smaller number on top. This is a reduction. -3 to +1 is 1/3. Everything is 1/3. So in this case, it looks like we have a dilation factor of 1/3. K, remember K is that number that we're multiplying each term by, is 1/3. Okay, so now we've got something a little bit different. Instead of having the coordinates, we actually have side lengths. So we're not looking at coordinates anymore, we're looking at side lengths. So this example says find the scale factor of the dilation of figure A to figure B, and then give the unknown lengths of figure A. So the first thing I want to do is I want to just ask myself, is this an enlargement or reduction? Going from A to B is definitely an enlargement. So I want to find my scale factor first. I know that it's going to be a number bigger than 1. So looking at the corresponding sides, it looks like the 3 corresponds to the 6. So the only numbers that I am given that I can compare, N corresponds to 8, and M corresponds to 10, so those won't be helpful. So let's go ahead and do our magic. Okay, so I'm having 6 and 3, and I need to compare them. I want a number bigger than 1, so I want to put the larger value on top and the smaller value on the bottom. So a ratio of 6 to 3 would be a dilation of 2. So now, in order to find N, I know that it corresponds to 8, and N has got to be smaller than 8. So I'm going to say that 2 times N would equal 8. So in other words, N is going to be 4. Just box up the dilation factor since that's in the questions. All right, so I have one more thing to find, and that has to be this M here. And the M, if you can't tell, corresponds to this side of the blue triangle right there. M Okay, now I'm ready to actually find some of these missing side lengths in figure A. So first, I've got side N. And side N corresponds to the side on B that says 10. So I'm just going to set that up. N is obviously smaller than 10. So 2 times N, getting the 2 for my scale factor, has got to equal 10, or N must be 5. All right, now let's find the last one. In this case, M. And if you can't tell, M is this side right here of triangle A. M corresponds to 8. M is obviously smaller than 8, so it must be 2 times side M, which equals 8, or M must equal 4. All right, so we're going to do the same thing with our quadrilaterals in B. So first of all, looking at A is this big blue quadrilateral, and B is the smaller red quadrilateral. Looks like we have a reduction. So in a reduction, we should have a K that's a fraction. It would be a fraction smaller than 1. So let's look at the sides we have. The only sides that we have that we can compare are this 12 and the 9. So again, we want a fraction that's smaller than 1, so we want the smaller number on the top and the larger number on the bottom this time. So in this case, the 9 is going to go on top, the 12 is going to go on bottom. We can simplify that to 3/4. And we have to find all of the unknown values in figure A. Well, there's a couple of things that we can do right off the bat without too much work. So let's see. Let's go ahead and find Q. Q is on A. Well, I'm looking at figure B, and figure B has this side congruent to the side below it. Both of them are 9. And since A is just a dilation of B, that means that the side that's 12 here on top must be the same length as Q on the bottom. So we have Q without very much trouble at all. Q is going to be the same as 12. So we don't have to work very hard at that. I'll just highlight it with the same color pen. Okay. Now R and P are going to have the same measures because 3 on one side of this quadrilateral B is congruent to 3 on the other side of quadrilateral B. And since A and B are proportional, the same thing must be true for quadrilateral A. Opposite sides must be congruent. So we're going to take our side 3, and we want to enlarge it because I want to find side A. So what I need to say is, well, 3/4 of P, because P is the longer, I'm talking about P right here, 3/4 of P must equal that side that corresponds to it on the red rectangle, 3. Okay, so moving on, I notice that if I multiply by 4 over 3 and by 4 over 3, these fractions will cancel. And P is going to equal 4. P equals 4. And because side R is congruent to P, or measure of side R equals measure of P, R is also going to be 4.